All right, so in the last few sections here, we're going to look at just some specifics associated with how we could potentially improve our models. We're going to start off with the discussion of variable selection. So, for example, if you have a lot of predictor variables, you may want to try to subset out the best ones to run your model. All right, so just if you were thinking about this conceptually, you would think that if the more information you gave an algorithm, the better it will do. So for example, if you were a doctor and you're trying to make a diagnosis, the more information that you can get about the patient's symptoms and body chemistry and blood chemistry and whatnot, the more likely it is you could come up with a good diagnosis. So this idea that information is power. But it's been shown that in the world of machine learning, that's not necessarily true. So looking at this graph from this manuscript by Jane et al., we can see a very interesting pattern. So here we have the classification error, and then this is the number of features on the x-axis. The dotted line represents training on 1,000 examples, whereas the solid line represents training on 100 samples. So for both lines, we see a decrease in error initially, and then the large sample size tends to decrease and then eventually level off. In contrast to that, the training with the smaller sample, it eventually levels off and then it begins to increase. So the model's actually doing worse as more features are supplied to it. So that seems counterintuitive. So the logic behind this is that if you have more features, then you have a more complicated feature space in which you're going to have to solve a problem. So you're going to need to have more training samples in order to fully understand that feature space. So what causes this really is an increase in complexity that isn't being offset by a large training set. So in short, especially when you have smaller training sets, it might be that you need to subset out some of your variables to have the best model that you can get. This is known as the Hughes phenomenon, as it was originally mentioned in this paper back in 1968, or the curse of dimensionality. Okay, so there's two broad ways that we could attempt to reduce our feature space. So one option is feature selection. So the idea here is to pick from the currently available features. So you're not creating new features, you're just subsetting ones that you have. So for example, if you have a hyperspectral image with 100 bands, you're just subsetting out a set of those 100 bands. You're not creating new bands. In contrast, feature reduction methods tend to actually create new data from the original data. A good example of this would be principal component analysis, where you're creating decorrelated variables from the original variables. Okay, so looking at feature selection methods, within Caret there is a recursive feature elimination tool built in that is based off of a couple different methods are used, but one method uses random forest. So here's an example of setting that up. So first, models fit to all predictors. Then each predictor is ranked using its importance in the model, again, generally assessed using random forest. Then you basically remove those least valuable features iteratively and continue the process, and then assess the accuracy on the different feature subsets. So here I'm setting that up. So we're using RFE control, which is recursive feature elimination control. We're using the RF functions, which is a random forest implementation. We're going to use cross-validation to actually perform the assessment with 10 folds. And so that sets up controls for that. And also you can see that I'm setting a random seed here, so I get the same result each time. And then this toSet, we're creating a sequence of 1 through 147 by 5. So the idea is we're going to test numbers of values from 1 to 47 every 5. And then here we're actually setting up the model. So we have, again, setting a random seed for consistency, reproducibility. So this RS result, we're calling the RFE model, RFE function. We set up our X variables, our Y variables, our sizes as defined up here. We're going to optimize relative to kappa. We're going to use the methods defined in the controls as defined there. And then at the end, we can do selected equals predictors of the model, and that'll spit back the feature space that was selected to be optimal. There are other methods. Another method that I like to use is the random forest model selection method that's made available in the RF utilities package. It's kind of similar, but it just makes use of a different process for using random forest-based variable importance to estimate variable importance in the optimal model. So again, there's multiple ways to do this. As an example of feature reduction, we can talk about principal component analysis, which you may be familiar with if you've had a statistical course, or maybe in remote sensing, because we can create principal component bands from raw image bands. So this is considered an orthogonal transformation, so like at right angles to each other. So you convert in-correlated variables into uncorrelated variables. And the idea here is basically that variance is information. So if you capture the variance and remove the correlation as new data, then you're actually just capturing the information content of the original data. So generally, variability in the data are described in a smaller number of principal components, thus reducing the number of needed variables. So in this example, this is two variables, so variable 1 and variable 2, and there seems to be a bit of a positive trend in the scatter, which suggests that there is some correlation between variable 1 and variable 2. So we basically transform it such that we basically transform the axes to principal component 1. So again, it's along the fit line so that it takes away the correlation, and then the second principal component would be at right angles or orthogonal to it. So again, we're producing uncorrelated variables from the correlated variables. Okay, and then what that will produce are eigenvectors. So this is what you have to multiply each input by in order to get that principal component. So for example, this is a set of principal components in the columns, and these are the original data layers. So basically, to get principal component 1, you would take the value in this layer, multiply it by this, add to it this value multiplied by this, and so on and so forth, and then that will eventually sum to the PC1 principal component 1 value. And then there's just different values or eigenvectors for each principal component. So again, these are the values that you need to create. The values need to create principal components from a linear combination of the input variables. We call these linear combinations because it's literally just the value multiplied by a coefficient plus the other value multiplied by a coefficient, so on and so forth. This is an example of the amount of variance within each principal component. So as you can see, that we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 principal components. The majority of the variance is contained in the first principal component, followed by the second, third, fourth, and then by the time you get out here, there's very little information, again, if you're assuming variance is information in the prior principal components. So we can go from a large number of variables to a smaller number of variables that actually captures the variance or information content. This type of plot is known as a scree plot. So there's different ways to do principal component analysis in R. One option is the PRC comp function PR comp function from the stats package. So in this example, I'm calling that on data. So we have a data object, and we're calling the function on it. And scale is equal to true means it's going to scale all the data so they're the same scale. And then from that, we can plot out the scree plot, get the eigenvalues, and just generally assess the new feature space. There's another option, I'm not going to go through an example, but just to mention, is canonical component analysis. So this is similar to principal component analysis, except that the new variables are created using the class signatures. So you're actually looking at creating a feature space that differentiates the classes as opposed to just removing correlation in the variables. So again, the goal is to create a feature space in which classes are more separable. We're not going to show an example of that. I just wanted to note that that's an option. Okay, so another thing that could potentially impact your results is training data imbalance. So it's been shown that most algorithms will be biased towards the class that has a larger number of samples. And many problems that we deal with can have extreme imbalance. So for example, if you're looking at fraud fraud rates on credit card transactions. The vast majority of credit card transactions are legitimate transactions. So if you actually took a random sample, you would have probably maybe tens or hundreds of thousands of legitimate transactions for every fraudulent transaction. So that would bias the algorithm toward saying everything is just legit transactions. So if for example, if you had a landscape that was 1% one thing and 99% the other thing, then the algorithm could just call the whole landscape the other thing, and it would be 99% accurate. So this balancing issue can be problematic when we're trying to train our models. So again, this is the idea. So if the trained data are not balanced, the algorithm may underpredict or poorly predict the less common classes. And that's been shown via experimentation. So how can we deal with this issue? So one option is to create a stratified random sampling so that we have an equal number of samples in each class, regardless of their true proportion in the population or across the landscape. That could be hard to do, especially if you have one class that is just very uncommon. So it might actually be hard to randomly select those in a stratified way. Another option is to randomly undersample the majority class, so just artificially reduce the number of majority samples. Another option is to duplicate the majority class example, so just have more examples of the majority class. And then lastly, you could produce synthetic examples of the minority class, so having using some type of randomization plus the original data to create new examples of that less abundant class. So these types of techniques can be applied fairly easily in caret using the train control and setting a sampling option. So here are some of the common options. So down means randomly subsample the more abundant class. So that'll create a more balanced sample, but the issue is that you're going to end up with less training samples because you're effectively throwing samples out. Up means randomly duplicating samples of the less abundant class. So the idea here is that you're not really throwing anything out, you're just replicating minority samples so it sees the same sample more than once. And then this method, the synthetic minority sampling techniques, that creates synthetic minority samples from the original data by just kind of incorporating random noise and also using the actual minority samples that were provided. Okay, and then in this last section, we're just going to look at some pre-processing options. Okay, so a caret provides a wide variety of different pre-processing options to rescale the data or do some other transformation, and here are some examples. Again, this is generally provided in the pre-process argument within the train function. So you can do box-Cox transformations, you can do power transformations, subtracting the mean from all the values to center it. You can divide values by standard deviation to rescale. You can normalize the range. You can filter out highly correlated variables, automatically create principal components from the raw variables, and then create independent components. So there's lots of options. All right, and then on this last slide here, this is just an example of center and scale, which I find is the most common data pre-processing that I do with caret. This is specifically important for KNN and SVM as they need to have data on the same scale. For tree-based models, it doesn't tend to matter as much. So in short, this is how this is done. So we have this pre-process argument that is inside of the train function, and in there we're calling as a list of a vector list of arguments that we want them to be centered and scaled. And then it'll do that pre-processing before the data are used in the training, and also again for any data that is predicted using the model in a later run. Okay, so this sums up the background section on machine learning. So now we're ready to move into actually doing some machine learning using random forest package and the caret package in R, and then predicting out to validation data and even to spatial data. And that'll be basically the rest of this course.